We've arrived at our final topic for this lecture series, which is thermodynamics. Thermodynamics is very commonly asked on many exam questions, and it's often also seen as potentially one of the more confusing topics because we're really going to shift the way we think about things, but I'm going to try my best to tie this to what we've been talking about in the past with work and with energy, and we'll see that this is actually not so foreign. We're going to start with this first lecture on just the basics, and we're going to ask what quantities can we measure about a system. So if I just have some container that has a gas in it, what quantities could we measure about this system? We already talked before when we were discussing gases that we could discuss the pressure, the volume, and the temperature of a system. These quantities, the pressure, the volume, and the temperature, are called state variables. The reason we call them state variables is that these quantities only depend on what the state of the system is right now. So for example, if I just walked into the room and I wanted to measure these quantities and I didn't know what you were doing with your experiment beforehand, I could look at exactly this beaker with whatever it has in it, and I could measure its pressure, its temperature, and its volume because these quantities only depend on exactly what the system looks like right now. And on the other hand, we could think of a counterexample to this because you might think, well, in this case, what isn't a state variable? But a good state variable might be a quantity that we'll be using a lot in thermodynamics, which is how much heat you've added to a system. So for example, if I showed up into the lab right now and tried to discover how much heat you had added to this particular system, there would be no way for me to tell. There's no way I could tell just based on the state variables of that system how much heat had been added if I didn't also know something earlier about the way the system had evolved and developed to the current point from where it started. So a state variable, again, is something you can always measure just based on the current state of a system and includes the pressure, temperature, and volume. The first sort of law we have to discuss is sometimes called the Zeroth Law of thermodynamics because it simply defines for us an idea of what temperature means. For the Zeroth Law, all we say is that if two systems are in thermal equilibrium with each other, that means that if these two systems, say 1 and 3, were in thermal equilibrium with a second system, maybe system 2, then they would by definition be in thermal equilibrium with each other. So this is our Zeroth Law that actually imposes this as a constraint or a definition on what we mean when we say temperature. That if two systems are in equilibrium with a third system, then those systems, like these ones, 1 and 3, would then by definition be in thermal equilibrium with each other as well. The first law of thermodynamics, as we go through the few laws that we'll be introducing, is that energy is always conserved. So for example, if we have a system here and it's a closed system, so we have a box drawn around it just to represent that you have some closed system, the energy within that system has to be conserved. This does not mean that there cannot be energy going into the system and energy leaving the system, which would change the energy of that system. What it does mean is that in that particular system, you can't be losing energy or gaining energy without the influence of outside sources. So again, energy can come into and leave systems, but only because of outside sources. You cannot gain energy or lose energy just by changing something about the system itself. The internal energy of a system will be representing with the letter U. So as we go, be keeping track of the different variables that we introduce. We've already talked about the pressure, temperature, and volume, which we have variables for, P, T, and V. So now we're introducing a new variable, the energy of our system, and we'll be calling this energy U, a capital letter U.